Welcome to the session 3 of Fluid Mechanics, Unit 3, Dynamics of Fluid Flow. In the last session, we have derived equation for venturimeter, that is discharge equation. Let us solve problem on the venturimeter. The problem is as like this. The inlet and throat dia of the horizontal venturimeter is 30 centimeter and 10 centimeter respectively. The liquid flowing through the meter is water. The pressure intensity at inlet is 13.734 Newton per centimeter square, while the vacuum pressure head at the throat section is 37 centimeters of mercury. Find the rate of flow. Assume 4% of differential head loss between the inlet and the throat section. Also find the CD for venturimeter. See, in this problem, we need to determine the rate of flow. This is a different kind of problem. Where the loss is given, okay, and this is for a real fluid flow problem. Here in this problem they have given the inlet and the throat dia, that is d1 equal to 0.3 meter and d2 is equals to 0.1 meter. You need to convert the centimeter to meter, so 30 centimeter will become 0.3 meter and 10 centimeter will become 0.1 meter. So we can directly calculate what is the area 1 at 1 and area at the section 2 by using the formula pi d square by 4. And P1 is given, pressure intensity at section 1 is given. It is in centimeter. So if you convert this to meter square, you will get into 10 to the power of 4. Whereas in case of section 2, they have given the, see here, it is the vacuum pressure they have given. So you need to write this value along with the negative sign. Since it is 37 centimeters of mercury, it is not the pressure value, it is the pressure head value. So we need to multiply that value by specific gravity of mercury to convert the value to the liquid flowing through the pipe, that is water. And divided by 100 is just because to convert centimeter to meter. So we will get the pressure head, not the pressure head at the section 2, which is coming around 5.03 meters. Next, calculate what is the differential head value, that is H is equals to P1 by rho g minus P2 by rho g. So it is coming around 19.032 meters of water. And it is also given the head loss is 4% of differential head. So determine the head loss. After that, by knowing this head loss and the differential head value, we can directly calculate the CD value also. There is a formula. CD will be equal to square root of H minus HL divided by H. So it is coming around 0.96. Then calculate Q actual, which is CD into Q theoretical. So it is coming around 0.14 meter cube per second. Point to be noted that you should convert all the values to the SI units. If they have given in the centimeters, you have to convert it into meters. So here is the second problem. Find a discharge of water flowing through a pipe 30 centimeter diameter placed in an inclined position where a venturimeter is inserted. The difference of pressure between main and throat is measured by a liquid of specific gravity in an inverted U-tube manometer, which gives a reading of 30 centimeter. The head loss between the main and the throat is 0.2 times of the kinetic head of the pipe. See here also in this problem we need to determine the discharge where they given the pipe diameter, okay, and also they have mentioned it is a inclined venturimeter. See, since the pipe diameter is given, the throat diameter we can take it as half the diameter of the pipe. And also they have given the X value, that is 30 centimeter differential U-tube manometer reading is given. And since it is a inclined venturimeter, we have to refer case 3 and case 4 as I discussed in the last session. So the formula is like this. Okay, so you can calculate the H value, which is X into 1 minus SL by SH. SL is the liquid flowing, lighter liquid it is. Okay, SL is the lighter liquid and SH is the heavier liquid. So you will get the H value as 12 centimeters of water. And also they have given in the problem HL is nothing is 0.2 times the kinetic head. Kinetic head is V1 square by 2g. So it is 0.2 times of V1 square by 2g. You can calculate HL also. Okay. After that, you can calculate V1 as well as V2. By knowing this V1 and V2, we can calculate the discharge, which is equals to Q into V1 or Q into V2 by using the continuity equation. Next topic is orifice meter. So this is the orifice meter. Orifice meter is a circular disc which is having a circular opening at the center. This orifice is inserted in a tube to measure the discharge of a liquid. Okay, you can see here, this is the cross section of the pipe where the orifice meter is inserted, and a U-tube differential manometer is also inserted to measure the difference of pressure. So they have considered two sections, section 1 and section 2. Section 1 is before the orifice meter and section 2 is after the orifice meter at the vena contracta. This vena contracta lies just next to the orifice, and here you can see the flow is laminar. There is no disturbed flow, it is a laminar flow, and it is a device used for measuring the rate of flow, and it is the cheapest device compared to venturi meter, and orifice dia is kept 0.5 times the diameter of the pipe. Next is expression for rate of flow through the orifice plate. Here let us consider P1 is the pressure, V1 is the velocity, and A1 is the area of the pipe at section 1. Similarly, P2, V2 and A2 are the corresponding values at section 2. Now applying the Bernoulli's equation at section 1 and 2, we will get this equation. Okay. From this equation, since it is a horizontal one, the z values, that is z1 and z2, gets cancelled. So the above equation reduces like this. Here, h value is p1 by rho g minus p2 by rho g. We have taken it as h, which is equal to v2 square by 2g minus v1 square by 2g. Okay. So from this equation, let us get the value of v2, which is square root of 2gh plus v1 square. Okay. Now section 2 is at vena contracta, and as I said earlier, and A2 represent the area of the vena contracta, and AO is the area of the orifice. So then we have CC, that is coefficient of contraction, is the ratio of A2 by AO, where CC is the coefficient of contraction. So from this equation we can get what is the formula for A2, which is equal to CC by AO. Now again applying the continuity equation, A1 V1 equal to A2 V2, will get V1 value. Substituting this equation, equation 3, we will get the equation for Q. Okay, the above expression is simplified by using the value of CC. So we'll get the expression like this. Then we have CD is equals to this formula, CC into square root of 1 minus AO square by A1 square divided by square root of 1 minus CC square AO square A1 square. Substituting this CD value in the equation 4, finally we arrived equation for discharge, actual discharge of orifice meter, which is equal to CD into AO A1 root of 2GH divided by square root of A1 square minus AO square. So this is the problem on orifice meter. The orifice meter of dia 15 centimeter is inserted in a pipe of 30 centimeter dia. The pressure difference measured by Hg oil differential manometer on the two sides of the orifice meter gives a reading of 50 centimeters of mercury. Find the rate of flow of specific gravity 0.9, take CD as 0.64. So, DO is given, orifice dia, and pipe dia is given, CC value is given. So you can determine AO and A1 by using pi D1 square, DO square by 4 or pi D1 square by 4. X value is given by seeing the same case what we have referred for venturi meter to calculate the H value. The same formula is holds good for orifice meter also. Since here it is a mercury oil differential manometer, so the liquid in the differential manometer is heavier than the liquid flowing through the pipe. So we can use this formula H is equals to X into SH by SO minus 1. Here SH is the specific gravity of heavier liquid and SO is the specific gravity of lighter liquid. So I'll get the value of H. Similarly, Q actual, we have a formula. If you substitute that, you will get it as 0.1368 meter cube per second is the value of actual discharge of orifice meter. Next comes to the third instrument, which is using the principle of Bernoulli's theorem, that is pitot tube. So it is a device used for measuring the velocity of flow at any point in a pipe or a channel. And it based on principle that if the velocity of flow at a point becomes zero, the pressure increases at that point due to the conversion of kinetic energy into pressure energy. And the pitot tube, it is a glass tube bent at right angle as shown in the figure. So this is the pitot tube. It is a glass tube bent at right angle. The point 1, let us consider 2 points, point 1 and point 2. Point 1 is at the same level, both are at the same level, but point 1 is away from the pitot tube and point 2 is just at the entrance of the pitot tube. Okay. Next, V1 is the pressure, V1 is the velocity at the section 1. P2 and V2 are the corresponding values at section 2. And here H dash is the depth of the tube in a liquid and H is the raise of liquid in the tube above the free surface. Since both the points are at the same level, we can take Z1 and Z0 or Z2 will be equal. So in the Bernoulli's equation, if you apply at section 1 and 2, the Z value will get cancelled. Okay. And if you take the pressure head at the section 1, it will be P1 by rho g, and at the section 2, it is P2 by rho g. So before going to this equation, you have to apply the Bernoulli's equation. So then substituting all these values as I have shown in the above. Okay, so the last equation for velocity will be arrived, which is equal to square root of 2gh. So V theoretical it is. To get V actual, we have to multiply the velocity, theoretical velocity with respect to coefficient of pitot tube or coefficient of velocity. Thank you.